Okay, good afternoon or good morning, everyone, depending on where you're located now, or good evening. So it's my pleasure to introduce Alexandre Seuret. Yeah, I don't think an introduction is needed. So everyone knows Alex as one of the young driving forces in the community. Also someone with a broad interest and very influential works. He's also someone who's very visible and with a very international profile. So he has had positions in Lille, KTH, Grenoble, Toulouse, and now in the Universitat de Sevilla. So we're very happy to give the floor to you, Alex. So I guess that you will talk about the role of orthogonal polynomials in the context of time delay systems. So you have the floor, Alex.
Okay, so thank you, Wim, for the very nice introduction. And also thank you for the organizer to invite me to present my works on time delay systems. So what I will do today is give an overview of what I have been doing on this topic for a couple of years, like almost 10 years, which is related to the work on Legendre on the links with between Legendre polynomials and time delay systems. So as you mentioned, so I'm now with the University of Seville, and this work was also done. Most of the part was done when I was at last CNRS in France. So in this talk, I will mainly talk about this simple system. So it's a linear time delay system that is driven by this equation. So you have the delay term that is here. And so this class of systems appears in many applications in biology, robotics, network control, and so on and so forth. And it has been an interest for many researchers because it represents an example, a simple example, let's say, of infinite dimensional systems. To see that, you may have to look at the fact that for this example, this simple example of one dimension, that depending on the value of the delay, you may have behaviors that are usually encountered when you have multiple poles. In these figures, like you see that this oscillatory behavior is something that is not expected for systems of first dimension, of dimension one. Another solution, another way to see that it is infinite dimensional, if you take the particular value of a delay h that is equal to pi over 2, you know that there are two solutions to this simple equation that are sine and cosine functions. And you end up with two solutions that are able to cross, which means that it somehow contradicts the natural theorem of uniqueness of solution to differential equation. But in the sense, when you have non-delayed systems, in the case of delay systems, the function is not, the state is not a point, a vector considered at some time of t, but it's a function that is considered over a period of time. And also you may look at the roots of this equation, that these equations have an infinite number of roots. So, as I said, this simple object has been been the subject of many researches, and you have many surveys and many books that are treating this problem. And in this presentation, I will mainly talk about two aspects. One issue that is related to the Lyapunov argument, and that stability analysis using Lyapunov argument, and leading to LMI tests or tests that are not necessarily LMIs. So the thing is that if you look at the literature on time delay system using the application of Lyapunov-Krasovskii theorems, so the process is always the same, or more or less. That is that you have to select first Lyapunov-Krasovskii functional or a candidate, Then you compute its derivative along the trajectory, and you try to express this derivative as a quadratic term that depends on a matrix pi that has to be definite positive to guarantee the satisfaction of the Lyapunov-Krasovskii theorem, and on a vector psi that is a vector that collects the information about the time delay system. As I said before, time delay systems are infinite dimensional systems, which means that when you do this operation, you have to somehow discretize the information about the delay function, about the delay state. So you cannot write here some functions respect to some parameters. So you have to find a way to discretize the information about the state. And so the objective of many papers has been to derive less and less stability conditions for this class of system following this process. And why it has been popular? It's because you have a lot of degree of freedom in this procedure, in the design of the functional, and also in the derivation of the LME condition. And as I said, you have this vector here that can be computed in many ways. So the problem now is to decide how to choose good Lyapunov-Krasovskii functional and good vector psi that collects the information. And so this has been the subject of many papers. And as I said, let's say that during the COVID, I received this picture to say to tell us about the types of paper in control theory. And when I look at it, I have first a good laugh, and then I was a little bit of ashamed because I fit in a lot of these boxes. And so you have many traps, and you have to be careful in order to provide good good papers and good contribution to those papers. So in this presentation, what I will do, I will try to not fall into the previous traps and try to convince you that there are some smart way and efficient way to build Lyapunov functionals and LMIs. And so I will start.
Alex, the previous slide, from which information is it?
Sorry?
Where have you found all this?
So it was an exchange on WhatsApp. So I just got it like this. And I had it and find it very funny. And so I wanted to share it with you.
Mm-hmm. Okay.
So this is an outline of my talk. So first I will review some works on Lyapunov-Krasovskii functionals. Then I will present recent works, so a contribution about integral inequalities with the application of Bessel inequalities. And then I will show you how to apply these inequalities to derive stability conditions for time delay systems. Then I will talk about some modeling issues that are related to the Bessel inequality and Legendre polynomials, and I will draw some conclusion at the end of the talk. So when you look at Lyapunov-Krasovskii functionals, so you have the main, let's say the first theorems that provide a general form of Lyapunov-Krasovskii functional that was provided in the work of Kharitonov and co-authors. And so this functional takes the form of a quadratic function which contains a lot of terms that involve the state of the delay function. So in this formulation, x subscribed t of s represents the state of the function of the time delay system, which is the vector of x of t plus s, and when s vary between within the sampling interval, the delay interval. So in this case, you have several parameters to find, p, q, t, and s, that are either symmetric positive matrices or differentiable functions to be considered. And in the work of Kharitonov, there were a very nice result explaining a necessary and sufficient condition for the existence of a Lyapunov-Krasovskii functional, that is the following. So you have the same class of functional, but that is driven by a function U, which is called the Lyapunov matrix. And the Lyapunov matrix has to verify the following inequalities, or the following equalities. So these are differential matrix differential equalities. And why is it working well? It has been built to satisfy this condition, meaning that the derivative of the Lyapunov function has to be negative within this constraint, and integrating the functional, you end up with this formulation with a U matrix that verifies this condition. And so what is really nice with this formulation is that it is an equivalent result that shows that if the system, the time delay system is asymptotically stable, then this functional V of U has to be positive definite for all the possible state vector. So it can go further because it is possible to find a solution to this matrix differential equation. So this was the work of Kharitonov that provide an analytic expression of this function that is defined as follows. So it's somehow a sum of exponential terms. And all these terms depends on the characteristics of the matrix of the system and on the delay. So you have to note just one thing that will be important in the next part of the presentation is that this function is continuous, but it has discontinuity in the derivative of this function of U. So the good thing is that so this is a constructive theorem that tells us about the existence of a Lyapunov-Krasovskii functional and how to build it. But now we would like to do some tests and evaluate the stability of the system. And several works so exploit this framework to assess some conditions about stability condition. So this is the work that is summarized in the recent survey of Sabine Mandier, Alexei Gerov, and Marco Gomez. And I pick two examples. I mentioned two examples of solution and only one theorem. And so this theorem says that if you can find an integer R that is greater than 1, such that this matrix is not positive definite, then the system is unstable. So this condition can be seen as a necessary condition for instability. Sorry, so it's for stability, and it ends up as an estimation of the point where your function is when your system is unstable. And how does it work? So you compute this matrix. And I give some examples for R equal 1, 2, and 3 of how to build this matrix. And you just have to check the eigenvalues of this matrix to verify if the system is unstable or not. And what is really nice also is that more recently, they transformed their necessary condition into a sufficient condition of stability, which means that the time delay system is asymptotically stable if and only if this matrix with a particular R that is given, that is a function of the matrix of the system and of the delay. So if this matrix is positive definite for this given R, then this system is asymptotically stable. So this is a necessary and sufficient condition. So one may say that, so as a conclusion, for up to now. So these are necessary and sufficient conditions for time delay system, and the authors of this contribution have extended this to multiple cases, such as multiple delays, distributed delays, and neutral systems. So you may say that now the problem is closed and we do not want to do something else, but still the problem that we wanted to know, to understand if can we have the same kind of result with LMIs. So can we have a kind of necessary and sufficient conditions based on an LMI? And another proposition is to improve this necessary and sufficient condition. So to do that, let's go back to LMI and to this framework. So what I will present now is related to the integral inequalities. So I have presented so far the complicated, the general form of Lyapunov-Krasovskii functional. But if you look back to the past, many researchers have been working on simplest Lyapunov-Krasovskii functional because you can end up with some LMI conditions. And so I took this example of Lyapunov-Krasovskii functional taken from a paper from Emilia. And how does it work? So you have this functional that is that involves this x dot term here, and you compute its derivative. When you compute its derivative with respect to time, you end up with this term that is in red here that do not enter directly into the framework of LMI because it's not exactly a quadratic term because of this integral there. So what you want to do in this case is to apply Jensen inequality in order to get a lower bound of this integral and to enter into the framework of the LMI. So how does it work? So Jensen inequality states the following things. So it says that for any function that is integrable and for any matrix that is positive definite, you have these inequalities that hold. What does it say? It says that the integral of a quadratic term is greater than a quadratic term of a quadratic expression of the integral terms. So it has been really popular for a long time in the context of time delay system. Why? This is because this inequality brings up this term which is related to the value of the delay. And when you end up with so when you compute the LMIs or when you derive the LMIs, this brings some terms that are, some LMIs that are delay dependent, so DD stability condition. But if you go deeper into the analysis of this inequality, the fact that when using this Jensen inequality, this is equivalent to bounding this expression in the complex plan. So if you look at the picture, this corresponds to bounding this blue area by the blue circle. Okay, so this means that when you are asking an LMI resulting on the application of Jensen inequality, you are guaranteeing the stability of the system when the uncertainty is inside this blue area, but also outside, inside the circle, which means that there is room for improvement, and this is what I will show you afterwards. So to understand and to give you an idea of how to do that, let us consider a simple proof of this Jensen inequality. The proof relies on the computation of this quadratic term. So this quadratic term is expressed as the difference of the x function, the difference between the x function and its mean over the delay interval. When you expand this expression, so you have the quadratic term in x that directly leads to this term. You have the quadratic term with respect to this term that gives this quadratic term here, and the cross products are also written in this form. So you end up with the very simple expression that corresponds that E is actually the gap of the, so this integral I, sorry, is the gap of the Jensen inequality. So a first solution that we provided in 2013 was to find a way to give a lower bound of this integral I. And this was possible by looking at Wirtinger's inequality. And using this Wirtinger's inequality, we were able to find some lower bound and giving some first solution to this problem. But finally, this was not the good direction, and we had to go to another things, which is related to the Bessel types of inequality. So how does it write? It is expressed as follows. So it says that the integral of x between the interval is related to a quadratic term, but instead of having just one term, one quadratic term on the right-hand side, we have multiple terms, and these terms are related to the projection of the state of the vector of the function x onto the set of polynomials, but not any polynomials. We looked at orthogonal polynomials, which are the Legendre polynomials for this case. So actually, so the idea of that is more or less the same as applying the Pythagorean theorem. We define an orthogonal basis of the functional state, and we project the value of the function onto this basis. And this expression basically says that the norm of the function, so the L2 norm of the function, is lower bounded by the norm of the projections. So the proof is actually very simple and corresponds to its simple extensions to the proof I presented of Jensen inequalities. So you have to compute the difference between x and its projection, so somehow its coordinates in the basis of Legendre polynomials. So basically what you get here, when you expand it, you have again the quadratic term in x that remains the same, and the cross term between the numerous polynomials. Actually, they are 0 if the number is the same. So if you are projecting onto the same polynomial, Legendre polynomial, but if the order are different, the orthogonality guarantees that this integral is 0. So a lot of term vanishes, and it makes that this expression is very simple at the end. So what is really nice is that this expression already contains some optimality criteria, because this projection vector, so this projection function, let's say this one, is the unique polynomial of degree less than n that minimize the distance between the function x with respect to this inner product. So in other words, if you look at other matrices or vectors theta, and you want to minimize the value of theta so that this integral, you want to optimize the value of theta so that this integral is minimized, and this value, the correct value of theta, are this projection. Okay. And so there are many other versions of or extensions of this inequality. So some works dealing with auxiliary polynomials, or an expression that is based on the canonical polynomial basis. But these are already included in this framework. But there are also some different works that were providing in the work of Qianfeng, where he was able to not consider orthogonal bases, but also various any sequence of independent functions. You have also the case of multiple integral inequalities that was done in the work of Gierkowicz, and the extension to the case of integral inequalities on infinite supports. And recently also the case, the application of this kind of lemma to the case of discrete time summation inequalities. So if I go back to this theorem, so when I pick the term, the particular case n equal 0 and 1, I recover the Jensen inequality and the Wirtiger-based inequality. And what is also very nice is that you have this Parseval identity, which says that this integral here is actually equals to the limit when n goes to infinity of this quadratic term. Okay, so this is something that says that the more you improve n, the more this inequality will be accurate. And more recently, we have used the link of with polynomial approximation, because if you have some smoothness properties of the function x, so basically the function f is continuous, and if it has continuous derivative over the delay interval, then the Legendre approximation converge. The series converge uniformly to its generator. which means that the distance between x of s and the evaluation of the approximation here is bounded, and this bound is uniform over the sampling interval. What is also very nice is that if you have some constraints on the derivative of the function x, you may also have, for an expression of the n, so the value of n, that guarantees that this equation is verified for a given epsilon. So you have n, an expression, an analytic expression of n that depends on the epsilon. So this is just an example to show how it works. So you have a function f that has to be approximated, and you can see here that with the first approximation, you have something that is converging very fast to the desired function. So let's see now how this framework can be applied to time delay systems. And actually, so I won't go much into the details, but we have provided this first theorem. So this first theorem is a sufficient LMI condition for stability, and it is expressed as an LMI. And you can see here the structure with S, 3S, and 2n plus 1 times S, and the same for R, which result from the application of Bessel inequality. And so I won't give you the expression of this, but so you can find it in the paper, but the idea is the following. So you have a proof that is based on a Lyapunov-Krasovskii functional. And this Lyapunov-Krasovskii functional is expressed using these terms that are the same as in the complete functional that has presented before based on the Lyapunov matrix, and some other terms here, which is quadratic, and this term depends both on x of t and also on this projection. So you compute the derivative of the Lyapunov-Krasovskii functional, you apply the Bessel-Legendre inequality, and then you conclude on the application, using the application of the Lyapunov-Krasovskii theorem. So this is another LMI dealing with time delay system, but it has some nice properties. First, it is convex respect to the matrix that defines the system, which means that when the matrices A and AD are uncertain but bounded or embedded in some polytopes, for instance, you may assess robust stability criteria with respect to this uncertainty. And you also have the same property with respect to H. So these LMIs are convex with respect to H. So unless this term here, but the other one are convex, which means that if you have this LMI that is verified with the same matrices P, S, and R for two values of delay, then this means that it is valid for all values of delay between the two delays. So what about complexity? So if you look at the expression here, so the number of decision variable increase with n. So each time you go from n to n plus 1, here you add a line, a row, and a column each time you increase n by 1. And the size of the LME is also affected by 1 when you increase the discretization, the polynomial order. So what is really nice is that actually this condition is very competitive respect to other stability conditions. I decided to not show the table showing the numbers and the decision variables. I prefer to show so some plots that will arrive afterwards. So, but the thing is, so we say that this condition, this theorem is depends on n, and we would like to know what is happening when n grows. And we have the following theorem, which says that so the set of delays for which you can find a solution to the LMI condition at order n, so you call it Hn, and you have this following, you have the following inclusion. So which means that the set of allowable delay that you have obtained at order n will be included in the set of solutions delay that are solutions to the LMIs at the order n+1. So how can you interpret this in terms of in a more illustrative way? So we pick this example that is taken from these papers. And it's a quite a complicated system in the sense that it has 4 dimensions and it has some very tricky stability regions. So stability regions are the areas that are in not in gray in this plot. And in colored, you can see here the regions Hn that have been computed. So this is H0, so the solution of the for the region where you have a solution to the LMIs at order 0, at order 1, 2, and up to 7 here. And so you can see from this figure that it gives the impression that you are somehow blowing a balloon. So, and you are, each time you increase the n, your stability region or your estimation of the stability region is going closer and closer to the instability region, and it is filling up the space here. So another interesting point here to see in this figure is that you have this tricky region that is hard to evaluate, because you have a stable part, unstable part, unstable part, and unstable part, so on and so forth. And you can see that when you increase the order, you are able to recover this region and to recover this region too as well. You may also see here some the fact that the curve here is not really regular compared to the previous order, and this is related to the computational complexity of the problem, because for n equals 7, then the problem, the LMI problem start to be complicated. So here we have shown that when you increase n, you get larger stability region, but we do not say anything yet about the convergence of the LMI. And we have, thanks to the work of the recent work of Mathieu Bajodek, who was doing the PhD with us until last year, which gives a convergence of the sufficient theorem on the convergence of the sufficient LMIs condition. So how does it read? We say that the system, the time delay system is asymptotically stable. That if the system is asymptotically stable for a given delay, then we know we have a proof that there exists an order n star and a solution to the LMIs, so to the decision variable, so Pn are in S, such that the LMI conditions are verified. So I will just discuss about the proof. The proof is very technical, but I just give you the sketch of it. So it starts with the computation of, not the computation, but the consideration of the complete Lyapunov function defined by the Lyapunov matrix U, and you define it for any given W matrices. Then what you do, you build the parameter of the Lyapunov function that you build for the Legendre case, based on the Legendre polynomial approximation of the Lyapunov matrix. Then you compute the difference between the Lyapunov matrix at order n and the complete one. You get some terms that represent the error of approximation. And then at the end, you use the uniform convergence of the Legendre series of U to U to show that these terms are uniformly bounded and tends to 0 uniformly as n tends to infinity. And this holds for all vector x, for all function x. And at the end, you pick particular function xt to conclude on the satisfaction of the LMI. So this is the big picture of the proof, but each part takes a couple of pages to be a couple of calculations to be satisfied. So we were also able to do go further and to provide finally necessary and sufficient condition, LMI condition. And this is due to the fact that, as I said before, when you use Legendre polynomial approximation, you are able to find an estimation of the order to get the estimation as close as you want. And so at the end, we were able to find an estimate n star of the order that is necessary to verify the LMI condition. So, and this function is a complicated function of the delay and the matrix that define the system. So finally, we have this nice result. So is provisionally accepted in Automatica, not yet accessible. But so the bad news is that these orders are quite pessimistic. So if I go back to the previous example and I try to estimate the values of n star so that we get this necessary and sufficient LMI conditions, the orders are really large. And from the computational point of view, it's definitely not reasonable to employ that. But at least we get this, convergence result. So the thing is now, we had this issue about LMIs, and we said that so LMIs are good, but we were at the beginning of the talk, I talked about necessary and sufficient condition based on the complete Lyapunov-Krasovskii, and this is another thing that Mathieu did during this last year of PhD, which was to translate the result of Sabine Mondier into the framework of Legendre polynomials. And actually, Mathieu got this very nice result, which says that, which is a new necessary condition for stability of time delay systems, which states that we compute a matrix that is composed of the Lyapunov matrix U, and the projection of the Lyapunov matrix onto the Legendre polynomial. Okay, so this object here is a collection of Legendre polynomials, and this matrix here is just, let's say, the Gram matrix, the Gram-Schmidt matrix of the Legendre polynomial. So how does it work? So we use exactly the same argument as in the work of Mondier, Alexandrova, and Egorov, and so on. And it's result in estimating, in looking for a function which is x0, which is infinitely differentiable over the delay interval, such that the function, the Lyapunov function of this state function is negative. But the main difference with respect to this work is that we are using polynomial approximation and the Legendre polynomial approximation. So we end up with this function, this matrix Pn that is composed by the polynomial approximation of U. And continuing with the same idea as with for the LMI case, we can end up with some hierarchical necessary condition, which means that if you consider the set of delay for which this matrix is not positive definite, then this set at an order n, then this set is included in the next set for the order of larger with a larger n. And this is due to the fact that when you consider the matrix at order Pn plus 1, mass plus 1, you have the same matrix, the matrix Pn that appears here, and some additional terms that you don't care. And so if you know that the matrix Pn is not positive definite, then this matrix Pn plus 1 will definitely not be positive definite as well. And so it seems very nice, but we have a very complicated task, that is to compute these terms. So if you ask Maple or MATLAB to do that, then you can wait for a while, because this term, this U matrix is composed of many exponential terms, And projecting this, computing these integrals might be very, very complicated, and this one as well. But using the properties of the Legendre polynomial, we were able, and so basically Matthew was able to define some recursive equation to express the coefficient of this matrix Pn. So at the end, it's really much more complicated than the discretization process of Sabine Mondi and co-authors that I showed at the beginning. But we will see the advantages in the next slides. So if you look,
but may I clarify something? So you have to tune all this W, which you have for construction of U?
No, it's somehow independent of the. So you mean the U, right? The U.
U is constructed on the basis of the choice of W.
W, yeah, but it works for any W. For any W matrix. So whatever the W you choose, it should work. So maybe it's something that I did not write in the estimation of the orders, but the estimation of the order n star depends on the value of W. I will show that. So compared to what I presented before on the LMIs, here we are not estimating the stable region, we are estimating the unstable region. And you may see that for very small orders up to 12, you have almost all the regions that are satisfied. And so this is the same kind of graph that you can see in the paper of Sabine. But so what is really nice again with this framework is that we are also able to find necessary and sufficient conditions for stability of time delay systems, because we are able to estimate the value of n for which the condition has to be satisfied. Okay, so if you have, the process is the following: you compute the n based on this formulation. So as I said, this number also depends on W1, W2, W3. So you have this expression and you check the positivity of this matrix. If it is positive, it is stable. If it's not positive, it is unstable. And compared to the LMI framework, the order are much more likely to be computed, because it's not an LMI, so you are not testing an LMI with a lot of decision variables. This is an eigenvalue test. And you are checking basically the eigenvalues of a matrix of size 300, for instance, for this case. And this is just to say a word about the efficiency of the Legendre polynomial. So we compare this work with this theorem with the work of Sabine. And actually, we were able to find some very good estimates that are working well. And what is really important to note is that the time that is spent here is mostly due to the computation of these terms here, because the eigenvalue is not complicated to test, but the computation and the construction of the matrix here, it's much more complicated. So this is just to sum up the main difference between the LMIs and the positivity test. So from the LMI side, which is on the left, we approximate the stability region from the left of the figure. And for the positivity test, we do it from the right-hand side. So the good thing about LMIs is that you have some properties of robustness that are able to be assessed, which is not the case with the positivity test, but the positivity test has benefits of not involving decision variables and LMIs. And finally, we have this difference, this huge difference with respect to the estimation of the order for the necessary and sufficient condition for the LMIs and the positive tails that are very, very different. And this is because in the LMI formulation, we need to approximate the Lyapunov matrix U, which is not very smooth because it is only piecewise differentiable, continuous but piecewise differentiable, while in this approach, we are approximating a function x0 that is infinitely differentiable. So it is known that the convergence of the polynomial approximation of this kind of function here can be very, very fast. And this is why we get such a low order here. So now I'm done with this stuff, and I would like to present some issues about modeling and what we can do with Legendre polynomials. So doing some kind of transformation or changing a bit the vector to be involved, what we have seen, or what Mathieu has seen again, is that when you are using Legendre polynomial and Legendre projection, you are somehow doing some kind of Padé approximation of the delay operator. So this can be seen as follows, let's say, that you are replacing this delay operator as something that depends on some matrices. So these are the dynamics of the projection, and you do some kind of error. You create a new error that is not the original one, and you expand the finite dimensional part of the system. And what is really nice is that at the end you can show that this formulation is strongly related to the Padé. So what we have been doing with LMIs and Legendre polynomial is somehow is really related to what you do in Padé approximate. And as a byproduct of it, you may have also very nice properties, such that when you consider the poles of the Padé approximate, which are given by the pole of this matrix, you know that on compact set that are subsets of C, any compact set, the poles of this function, when n goes to infinity, converge to the poles of the real-time delay systems. And another issue is related to the modeling of time delay systems by using the interconnection of ODE, so ordinary differential equation, and PDEs. So looking back to the work of Miroslav Kristich on backstepping to provide the links between backstepping control and Smith predictor, you may rewrite the time delay system as follows, which is a linear system which has an entry U that is the output of a transport equation that is given by this part. So the question was to understand if we can use this model to derive some other to expand in a very simple way what I presented before to several classes of time delay system. And actually, so we consider in this case a case of multiple channels. So in this case, we have a transport equation which is composed of m elements. So U belongs to this. So is a vector of m dimension m, and it affects the dynamics of the ODE, and the ODE feed back to the transport equation. So in this formulation, you have this lambda matrix, which is which collects the transport speeds of the channels, and you may have different speeds and different velocities to transfer the information from one side to another side. And we were able to expand and to translate the previous LMI into an LMI of transport equation with an ODE. And what we get is a very similar formulation. So you can find a triplet of matrices that verify these commutativity constraints. And if the LMIs is verified, you can show that the coupled ODE and transport PDE system is exponentially stable in the sense of this norm. I'm not talking anymore about Lyapunov-Krasovskii theorem, because the Lyapunov-Krasovskii theorem applies only to time delay systems. And here we are talking about this norm. And the proof is very simple. It's based on the same Lyapunov-Krasovskii, Lyapunov functional, not Krasovskii anyway. And you apply Bessel inequality, and you apply now a Lyapunov theorem on ODE PDE systems. So based on this general formulation, we were able to apply it to several examples where you have multiple delays. So you have 2 delays or more, or you have also the case of cross-talking delays. So I took this example from a paper by Rifat Sipai, where you have terms that that are delayed by H1, H2, and the sum of H1 and H2, which makes a lot of complication. And what is really nice is that you just have to check to plug the transport matrix with the correct values. You just have to select the C and D matrices that explain how the delays are interconnected, and you end up with this simple formulation. And another issue is we can provide some ideas of how to discretize to provide some discretization LMIs for time delay systems by considering not only a single transport equation, but 2 or several transport equations. And at the end of each transport equation, you feed it back to another one, and the velocity is increased by 2. So in that case, you are doing some kind of discretization process of your system, and you are creating a Lyapunov-Krasovskii functional that is discretized almost in the same sense of Kekin-Gu result of discretization, and also in the sense of delay partitioning of James Lamb and so on. So by doing that, just changing the models, you have the same LMI and you are applying a discretization process. And when you look at the results, in this case, you may see here in this plot, so the efficiency, that is the vertical axis, respect to the number of decision variable. And each curve represents the value of different n. So you have n equal to 0 and n equals to 4 here. And the other plots correspond to the case where you increase the number of discretization in the sense that I presented before. And what you can see here is that when you apply the discretization, when you apply Lyapunov, the Legendre method and Bessel inequality, you go much faster to the desired efficiency, to the desired value, and with a very low cost in terms of decision variable. But when you do the discretization, you increase a lot the discretization of the space, of the delay interval. You do a lot, you increase a lot the number of decision variable, and you improve the stability condition, reduce the conservatism, but at the price of a very high increase of the decision variable, number of decision variable. So this drives me to the conclusion of my talk. So I talked a lot, and I hope that I did not go too fast or too slow. So what I presented here is related to integral inequalities, which are asymptotically non-conservative and that are based on Legendre polynomials. We have presented that these general inequalities are related to Jensen inequalities and Wirtinger-based inequality. We have something that is scalable and hierarchical. in the LMIs and in the results, and which say that when we increase the number of polynomials, we can only reduce the conservatism. And more recently, we had this necessary and sufficient conditions, and we prove that eventually, when you increase, you will get a positive answer. So what has been done also was to so many extensions related to some other class of Lyapunov-Krasovskii functional that involves the x dot terms, multiple integral inequalities, which was done by Eva Gierkowitz. And we have also considered this framework into the, for this method into the framework of quadratic separation. We have also considered the case of differential and difference equation with distributed delays with finite and infinite supports, and also some extensions to the case of discrete and continuous time with time varying delays. So from what I think about the next step about this case for what I think is that the main issue is now to understand how we can reduce this the estimation of the necessary order n that represent a very challenging issue that we would like to continue working with Mathieu. So we have done also other extension to the case of ODE systems that are coupled with different PDE systems. So I just show a couple of examples on heat equation and weight equation. And actually, the process is almost the same. So you have an ODE system that is connected to PDE with some particular boundary conditions. You build a Lyapunov functional that is related to this particular interconnection, and you include in the Lyapunov functional the projection as we did for the previous cases, and you end up with some LMIs that give you some estimates of the stability of the region of attraction. So we have done in this direction a lot of works to include some nonlinear cases. Such that system with saturation. So in this case, just a comment that usually when you have saturation, you want to estimate the basin of attraction of the system, because the stability is not global; it's only local. And using this framework of Legendre, we were able to say something like, if you consider you can consider initial conditions that are polynomial and say that the condition, the set of, so the basin of attraction is composed of polynomial function, let's say. We have also, thanks to Mathieu Barrault, another Mathieu that has been working on that, considering the case of a drilling system with a stick slip problem, and more general parabolic equation, and also thanks to Mathieu Barrault, the problem of IQC, so integral quadratic constraints using Legendre polynomials for PDE systems. So the last things I would like to say is what needs to be done, and I will just take the credits of Mathieu again, that is currently working with Giorgio Valmorbida and Ugo Lacemi on the extension of his work on the necessary conditions for time delay system to the case of ODE-PDE. And I have seen a paper dealing with the heat equation. I would like to see that more in details. And also to deal with another problem, which is the convergence of the LMIs for the ODE-PDE systems. And so that's it. And I will just give some acknowledgements to the main architects of this work, so, which are Mathieu Bajodek, Mathieu Barrault, Lucie Baudouin, and Frédéric Guesbeau, and also all the other co-workers that has been working on this area with me for several years. So thanks a lot for your attention, and I'm happy to answer to some questions.
Yeah, thank you, Alex, for the very clear and convincing talk.